we still have the. So today we are really, doing something exciting and truly exciting. So this is a real event that, things are so exciting. So let's get started. And the first thing is that last time we kind of get a definition of the Pascal's triangle. Pascal triangle is always one of your favorite topic in the counting and statistics. And so basically, it starts from a blank space where every grade is 0, then certainly there's 1. Then on the top layer, it began to multiply. So basically, the left fork and right fork multiply. Then multiply, then once they're converging, you just adding. So this is just the way you define it. And it was discovered independently throughout the history in China, Persian, and in Western math world. And so this one, it has several simple properties. And so a lot of time it was written in this format. This format of the this is binomial coefficient format. And we can also write in the normal format. Normal format is just 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So basically those are equivalent. And we see that it's actually equivalent to pass counting problem. So basically, the next pass is equivalent to the 2 previous possible pass in a grid situation. So basically, because the pass problem is a combination problem, and Pascal triangle addition is also has the same rule on addition of the previous layer of the node. So basically, Pascal's triangles are the combinations, binomial coefficient in truth are. So basically, this actually is not a coincidence. It is a well designed result, because they have the same starting point, they apply the same rule, so every step it will be the same. Then today we are trying to go through several of the interesting identity that related to the Pascal's triangle. So this basically, if you, this basically is just, on any node, for example, 1, 2, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So this basically, this little chapter or this little interesting combinatorial identity is just called Pascal's formula. So this is all called Pascal's identity. Sometimes it's called. So this identity basically just saying that, the top layer, it's a reverse triangle. So basically there are sum and addends relationship between this inverse triangle. And so basically, it is just, this relationship is actually quite simple. So the previous layer, the top layer has 2 numbers. The adjacent number of top layer added together to be the lower layers. Top layers adjacent number add up to the lower numbers. So from the left it's actually right fork. For the right number, it's left fork. So basically, the top layer adjacent number add up to the converging number of the lower number. So this is just graphic interpretation of the Pascal triangle, and it's fairly easy to basically this formula was written in a lot of formats. So if you use m or use other number, so basically to write this formula, it's very simple. You kind of just add equal to this. And this, for example, it does not has to be m minus 1. It does not has to be n. It does not has to be m plus 1. Basically, just the top layer and lower layer has difference of 1. For example, if I say that a plus 3, then a plus 3, and then here, for example, then below a plus 3, it must be a plus 4. So basically, it's just, then the top layer need to be adjacent number. For example, this is, for example, a plus k, like minus 4. Then basically, these are adjacent. So a plus k minus 4 plus 1 is minus 3. So basically, that will be equal to the right fork of the left number and left fork of the right number. So it must be a plus k minus 3. So basically, this type of the formula, you can always just write this way. For example, here basically it's just saying the top layer is n minus 1, then the lower layer is just 1 plus. And these are adjacent number. So basically, so this is the right fork of the left number. Right fork of the left number will plus 1, and left fork of the right number will keep its value, will be r. So basically, it's very easy to, so basically it's just 2 layer, the top layer and the lower layer, and then basically you will be able to do this very easily. And I'm trying to so those basically are very easy. And so 1 through 0 equal to 1, 1 through 1 equal to 1. So 1 plus 1 equal to 2 through 1 equal to 2. So basically, this is very easy to really double check. I think you can check the rest of those. And I think because those are so easy to check, I wouldn't waste time here. So basically, problem 12.7, it's just the rule of the combination is like, is this inverse triangle. So basically, if you can visually understand the Pascal triangle's addition rule, so this Pascal identity is, this theorem is just a mathematical representation of this addition rule of left fork, right fork converge to the next layers number, converging number. Then this number is proved algebraically. Prove algebraically, basically, so Pascal identity, they always ask you to prove in 2 ways. So let me just show, how do you prove 2 ways. So basically, this is n, and this is r minus 1 plus m r equal to m plus 1 r. So basically, you kind of just use the definition of it. And so this one, basically, this one, you are able to expand the definition. And so the definition, so basically it's using a minus r. So right now it's not using n, it's not using n minus r. Using n or n minus r, it doesn't really matter. Basically, if you use n, you just prove likewise. Basically, it's just plugging the definition. It's just plugging the definition. So the definition of combination number is the top is the factorial of the top number. Then the bottom basically is the factorial of the peak number, and multiply the factorial of the top number minus the peak number. So basically this is just flat replacement of this portion. And this is just definition flat, straightforward representation of this one. Then basically when you're trying to do this and you simplify it and trying to find the common denominator. And the common denominator, obviously, there's a, because this is r minus 1 and r factorial will be r minus 1 factorial multiply r. So basically, you actually is able to factor out some number. And then here, basically, it's cancel one side. First, it's cancel one side, because it's trying to cancel all the way to so basically you take the bigger of the factor, the bigger of, so r minus 1 factorial and the r factorial, this is the bigger factorial. This is, or this one, the lower one is the bigger factor. So basically we are trying to find a common factor. So basically, it's actually combining to this one. And then this number and this number, this is bigger factorial. So basically, it combined to this one. So for this one, because this portion already match, this portion I'm short of r. So basically for this term, I just multiply r. And for this term, basically the r factorial portion already matches. So basically all I did is just multiply n minus r, because m minus r factorial compared to m minus r minus 1 factorial is just one factor short. The short factor is m minus r. So basically it's just multiply m minus r on this term. So after doing this, basically we actually get the bottom part is actually the same. Then we just combine the top. And so the top portion from here to here basically is exactly the same, because we just, combine two terms into one term. And this portion basically has the same factor. So basically you can factor out this part. Then basically the other portion is just n minus 1 factorial multiply r plus m minus r. So r and minus r cancel. So basically, the top portion actually beautifully collapse into just n factorial. So basically, the top portion collapse into the n factorial, and the bottom factors are r factorial and n minus r factorial. So this way is actually just turn into the pure definition of n truths r. So basically, this is algebraically proved. It's really easy. So basically, it's just write out the definition in a combination form and find the common factor, or find a common denominator, then trying to add in with the common denominator, then the top term will collide into n factorial, then you will actually prove it. So this one is actually, has algebraic proof. Algebraic proof is just, manipulation of the terms, but then it has a reasoning proof. So reasoning proof is problem 12.9. So let's go through the 12.9. And Blair, would you try to read the problem until A?
So prove Pascal's identity using the following committee forming argument. Consider a club with n members, one of whom is Bob. How many R-person committees can be formed?
Yeah. So just for little problem A, how many way you can do this committee?
N choose R.
Yeah, exactly. So that's a flat n choose R problem. So Xinlai, could you read problem B and try to see, how to solve problem B? We cannot hear your voice. Xinlai, could you have you turned? Oh, yeah. We can hear right now. Yeah.
It's on. It's just I gotta switch it occasionally.
Oh, okay, good. Yeah. So basically, you say it's n minus r and choose r minus 1 exactly. So basically, if Bob is already in the committee, so the total selection pool will be 1 less. So it's n minus 1. And then also you don't have to choose R person. You only need to choose R minus 1. So exactly. So let's do problem C. That's Blair, would you try to read and solve problem C?
Okay. C. How many R-person committees can be formed which do not include Bob?
Yes.
So without Bob, then we have n minus 1 remaining club members. So that's basically n minus 1 choose R.
Yes, exactly. So basically, without Bob, you have smaller pool, so n minus 1 selection pool, and but because Bob is not in the committee has 0 person right now, you still tasked with selecting our members. So basically that's R. So basically then total way to select this committee is the sum of the way to select with Bob and without Bob, because with Bob and without Bob is a totally exclusive condition which will add up to the total. So basically with this reasoning, basically you can use logical reasoning saying that n truths are equal to n minus 1 truths are minus 1. That's including Bob plus m minus r and n minus 1 and choose R. That's without Bob. So basically, you know, this is just with reasoning. You are also able to make this same conclusion exactly. So let's get on to the another one. So another one is another interesting combinatorial identity is just basically each layer is actually, this is 2 to the 0th power, 2 to the 1st power. If you add it, this is added to 2 to the 2nd power, 2 to the 3rd power, because that's actually fairly easy to understand. And so basically it's just, you know, you see the power relationship. This is actually equal to 1. So basically, so it's actually 2 to the nth power, which n start from 0, because Pascal triangle level start from 0, not starting from 1. So that's the so Pascal's triangle, basically the nth row is n choose 0 plus n choose 1, add all the way to n choose n. So they are altogether, they are n plus 1 number. So at nth layer, you have n plus 1 number, because at level 0, you have 1 number. So basically, you know, it's always n plus 1 relationship. Those number will add up to 2 to the nth power. And this is easy to understand because Pascal triangle is actually, each layer you are doing left fork and right fork. Basically, you are doubling every element of the layer. So if you double every element of the layer, then their sum supposedly will be doubling. So they are, you know, just from the rule of the Pascal triangle, it's kind of self-evident. I don't have to spend a lot of time proving it. So this is just a way that, you know, and
Isn't 2 to the power of n basically just like, wait, like, isn't 2 to the power of n just equal to n to that?
yeah, 2 to the power n.
Yeah, but then like if you add these up, then shouldn't it be bigger than that?
No, it's just 2 to the power of n. It wouldn't be bigger than it's exact 2 to the power of n. Because think about it, the first layer is level 0. Level 0, it's actually 1. 1 basically is 2 to the power of 0. Then you double it. The second layer basically is level 1. So level 1, basically you do left fork and right fork. Basically you double the value of the 2 to the 0. So basically 2 to the 0 multiplied 2, which is 2 to the first. So basically, you know, it's very self-evident that at between each layer, it's always double the total count. So this layer, you add it, it's going to be, you know, 2 to the first. And then here, every number you are left fork, right fork, and basically, you know, this one get cloned because part of the one, you know, is here. You just see it by itself. Part of this clone basically merged into 2 because that's where the 2 come from. And the 1 plus 1 equal to 2. So basically, so and this element get doubled. This element also gets doubled. So basically between the first, between second layer and the third layer, it's actually doubled. So basically 2 to the first multiply 2, it's going to 2 square. So that's why it's actually 2 square. So basically, you know, it's very obvious that it's going to be every row, it's just exactly 2 to the nth. It's not going to be bigger or it's not going to be smaller. It's just going to be exactly 2 to the nth power. Does that make sense? And so this one thinks it's just, you know, a very simple relationship, and it's just using the Pascal top layer and the bottom layer addition rule, you can prove it. And this type of the proof actually is called mathematical induction. Basically, you have a base. So the base number is true because it's true because it's trivial. It's very easy to verify. You know, the zero level is equal to 1, which is equal to the n's, to the zeros. Then between each layer, your relationship is always double the value, because every element doubles the value, then eventually the sum will double the value. So basically, so you assume that the nth layer is the sum equal to the nth, then basically, because every element of the nth layer going to be doubled into the n plus 1 layer, so the n plus layer has to be 2 to the n plus 1 power, the sum. So basically, it's really easy to prove using mathematical induction. And so this chapter is actually quite easy. So I think we'll just do the homework here. Then we're going to push as much as on this problem 13, because Pascal triangle is the it's a hockey stick. So basically, right now so this chapter we're going to solve the rock and stick problem in a more troublesome way. It's a more dumb way, but it's not necessarily more dumb. It's just a more like the stick and rock problem. Actually, you think about this problem in a very smart way, so you can solve it. But how about, let's say you haven't think about this problem. You haven't think about solving the problem in that type of a smart way. Let's just tackle it using a normal counting method. How do we solve it that way? And this chapter actually provide a path. And then through the path, it's also going to tell you the story of the another Pascal triangle identity called hockey stick. And the hockey stick is very useful in some situation. So let's keep on going on this journal. And so the Pascal triangle, so the problem we are given is that 12 identical candy, and how many different ways can I distribute to candies to 4 different person? All the candy must be given out. So this one, after we learn the stick and rock problem, basically it's actually quite easy. You kind of 4 different kid is just, I need 3 bar, because 3 bar to divide the 4 different kid, because 3 bar create 4 slot. And then we have rock, so 12 rock. So 12 rock plus 3 stick. So it's actually will be 15 through 3. So this is an easy one. But basically, let's say that we are not using this. We are not using this. And let's just trying to solve it by brute force. Let's see how much troublesome it is. So basically, if we do it by brute force, and let's see that we can give all 12 candy to just the first person, or the second person, or the third person, or the fourth person. So basically, I have 4 ways to do it. So basically, we could give each kid 3 pieces. So that's one way. And we can give 5 to the first kid, 4 to the second, and 1 to the fourth. 2 to the second. So it's 5, 5, 4 to 1. 5 to 4 to 1 basically is actually is a permutation. So actually 5, 4 to 1, it could be ordered among 4 kids actually as a 4 factorial. And there are a lot of this type. So 5, 4 to 1, then there could be 6, 3 to 1, also 4 factorial. So if we really think about this way, it kind of will be fairly quickly we got ourselves confused. So we kind of had to pause a little bit. So let's pause a little bit and use a step-by-step approach to simplify the problem in a different manner. So basically the step-by-step approach is that when you given a complex problem like, 12 candy distribute to 4 kids, and we can treat the problem with 2 variables. So number of the candy and also number of the kids. So let's try. So we can say that we can try to fix the number of the kids to 4. Then trying to start from fewer candy, for example, from 0 candy all the way to 1 candy, 2 candy, all the way to 12 candy. So basically, if we reduce this problem into this fashion, this is one method. So then second method is that we can fix 12 candy, and then we vary number of the kids. We can have 0 kid, 1 kid, 2 kid, 3 kid, 4 kid. So basically, we have when you hit problem like this, basically you have 2 different approach to simplify the problem and trying to tackle it from different angle. So let's try to tackle it from the number of the candy angle. So how do we solve this problem? Let's say that let's start from 0 candy. If I have 0 candies, there's only one way to distribute to 4 kids. Because that's actually quite obvious. I have 0 candy, none of the kid will get any candy. So none of the kid get any candy, that's a result. That's a result, no matter how unhappy, how grumpy the kids are. I have no candy, that's the way it has to be. So basically 0 pieces easily solved. Let's go for 1 piece. So 1 piece for kid, and so 1 candy. Assume the candy cannot be divided. You cannot subdivide the candy. You cannot take out knife and cut the candy into smaller piece. You have to give it out as a whole. So when you have 1 piece, it can only give to 1 person. So kid 1, 2, 3, 4. So basically you have 4 ways to distribute the candy. Then let's see the 2 piece. So 0 piece is 1 way, 1 piece is 4 way, and the 2 piece. Let's see how do we handle 2 piece. And 2 piece, there are 2 general ways to divide the 2 different kids. Let's say that I gave both candy to a single kid. They are 4 way. So kid 1 get 2 candy, kid 2 get 2 candy, so on and so on. So you get like 4 way to do that. Then you can just give 1 kid to 1 person, the other kid to the other person. So basically, this problem became 4 truths too, because like it became the problem that I divide 4 person into group. Each group is 2 person. One group has the candy, the other do not has the candy. So this is actually 4 truths 2, which is equal to 6. So basically, 0 piece, 1 piece, 2 piece, it's easily solvable. Let's try 3 piece. So 3 piece gave to 4 kid. So we can, obviously, we can get 3 to all 4 kids, 1 of the kids, so that's 4 way. Then I can do 2, 1. And so 2 piece gave to 1 of the kids, 1 piece to give to the other kids, and then the rest of 2 kids do not have. So the order actually matters. Order matters became permutation. So basically, it's actually 4 permute 2, which is 4 multiplied 3 equal to 12. And then we can also do the like 1, 1, 1. So we have 3 pieces of candy and they distribute to 4 person. And this basically equivalent to 4 person dividing into 2 group. And one group have 3 member, the other group have 1 member. So it's actually 4 choose 3 equal to 4 choose 1 also equal to 4. So basically that's actually have 4 way. So 4 plus 12 plus 4 equals to 20. So I have 20 ways of doing it. And so far so good, still handleable. But let's say that so 0 piece of candy is 1, 1 piece is 4, 2 piece is 10 because it's 4 plus 6. Then 3 piece, basically this is 4, this is 12, this is 4. So basically that's 20. And it's already became complex. And let's say that if we have to go to 4 piece of candy to 4, then it's already became. So the key thing is that going down this path seems to be, you cannot build upon the previous case. Basically, there's one problem that the rule of the game changes quite a lot, because the first one 0 to 12 is just 1, and basically it's or 0 candy to 4 kids. And then 1 candy to 4 kids, this is C, 4 choose 1. And this is the first one is 4 choose 0. And then the second one, starting from the second one, there's a problem. It's 4 choose 1 for the 4 piece. for two piece concentrated on one, then 4 choose 2 for two piece distributed. Then here on the third one, basically it already became permutation. So basically because the order matters. So basically, you see a pattern change, and it's became unmanageable. So basically there just seems to be a path that you might not want to take. So so the rule of the thumb is that you don't have to have a tunnel vision to solve a problem. That so if you try something that do not work and seems to be changed dramatically during the process of accumulation, and you could back out to a different path. So let's try to do a different path. So different paths basically, because they are two variable. So we fix the number of the candy, and so initially we actually vary the candy. So the second approach is vary the number of the kid. Vary the number of the kid. Let's try to see that. Like first, let's say that I have 0 kid. So 0 kid basically, it's going to be undistributed. So basically, 12 candy will be giving out to no one. So that this is also one way. Basically, it's going to be sitting at maybe on teacher's desk. So then if I have one kid is 12. I need to give all 12 candy to one kid. So still one way. So if I have a 2 kid, if I have 2 kids, then basically I can have so they are kid 1, kid 2. 12 candy goes to the first kid, and the second kid 0. So I can make a table. 11 to the first kid and 1 to the second kid, and so on and so on. You can actually vary all the way to 0 candy to the first kid and 12 candy to the second kid. So basically there seems to be 13 ways. So basically giving out 0 candy is solved, 1 candy is solved, giving out candy to 2 kid also solved. It's not just solved for 12, it's solved for every number. So basically no matter how many candy, if it's 2 kid, it's the problem is solved. It's just number of the candy plus 1. Then let's say that, how about 3 kid? So 3 kid, let's break down the problem into let's build upon the 2 kid problem. Because if there are 1, 2, 3 kid, if I gave 0 piece of candy to the first kid, then basically it's going to be for kid between 2 and 3, kid 2 and 3, it's a 12 candy problem. So basically because this time so basically let me restate the problem. So we have zero kid. Basically it's just one way. We have one kid, basically is also all the candy need to be given out. So it also has one way. So only one kid, you just gave all the candy to that kid. If you have two kids, basically, for example, if you have 5 pieces of the candy between two kids, basically it's just 6 possibilities. So basically for the 2 kid situation, basically is n plus 1. N is the number of the kid. Now n is number of the candy. Basically it's just 0, 5, something like that. So for the 2 kid, it's also solved. N plus 1. So basically we already got 2 kid problem mastered. So we're going to take on the 3 kid problem. And for 3 kid problem, if we gave the first kid 0 piece, and right now we are looking at a 3 piece of candy. So it's not 12 piece of candy. It's just 3 piece of candy divided upon 3 kids. So basically it's 3, 1, 2, 3. We have 3 kids and 3 piece of candy. So I gave the first person a 0 candy. So between 2 and 3, between kid 2 and 3, they are dividing up 3 candy. 3 candy actually has 4 way. So basically, this is actually, so this is the, so I'm going to change the colon to number of the remaining candy. So basically, so you can completely list them out. So 0 candy for the first person, you can 0 for the second one, and 3 for the third one, and 1 for the second one, and 2 for the, so basically you can complete listing them out. So basically they are 4 way. 2, 1, and 0, 3, 0. So basically, this is actually 4-way. So basically, this is actually combined to 4-way. So 0 will be 4. And then 1, if the first kid get 1 piece of candy, then you can 0 for the second one. And so you have 2 pieces of the candy. So 2. And 1, 1, 1, 1, 2, 0. So basically combined together, they're actually 3-way. So basically, so this is the first column, this is the last column. So if we just focusing on those 2 columns, the first column is number of the candy I gave to the first kid. Then the third column is the combined ways I can have for the second and the third kid. Actually, it follows this pattern. 0 will be 4, and 1 will be 3, and 2 will be 2, and 3 will be 1. So 3 basically just means that I gave all 3 candy to the first kid. Then for the last 2 kids, basically they both get no candy. So that's only 1 way. So basically, this actually became 4 plus 2, 4 plus 3 plus 2 plus 1. So basically for 3 candy among 3 kids. So basically, we actually solve the, 1 kid, 2 kid. 2 kid basically is n to n plus 1. Then basically for 3 kid basically it's actually n plus 1, because that's 4 plus n plus n minus 1 all the way to plus 1. So basically it's became a series. And this basically is n, they are basically n plus 1 number. So n plus 1 plus 1. You average it, then multiply n plus 1. So basically it's actually n plus 2 and n plus 1 divided by 2. So that's the formula for 3 kids, if you put it generally speaking. So basically is n plus 1 multiply n plus 2 divided by 2. So basically, so right now we actually find that if we vary the number of the kid, it's actually accumulable. So 1 kid is 1 way, and 2 kid is n plus 1 way. That's the number of the candy. N is number of the candy. And for the 3 kids is actually n plus 1 and n plus 2 divided by 2. And actually is equal to n plus 2 choose 2 way. So basically, that's actually is buildable. So right now we are going to do the number of the 4 kids. So right now it's actually a full table of the 4 kids. The full table of the 4 kids is actually, if I have 0 candy gave to the first 2 kids, then the number of the way to give to the 3 kids. 3 kids, we already had the formula n plus 2 choose 2. So 12 candy. 12 candy basically is n plus 2 is 14. 14 choose 2, which is 91. Then basically, I gave 1 piece of candy to the first kid. Then 11 remain to be distributed. 13 choose 2. So basically, you actually can make a table. So basically, if we go this path, it's actually doable. So basically, eventually what it will get is actually this number. If you add it, you actually going to be 455. So 455, that's a very interesting thing. And then we can also make a table, number of the candy, number of the kids, and make a table. And make this table, then make a table, do some observation. Let's see that. This is number of the candy, number of the kids. So if you have only one kid, no matter how many candy, there's only one way. You just get all the candy. So that's one. If you have two kids and dividing the candy, right now it's actually um, 0 candy has one way. 1 candy you have two way. You can give either kid 1 or kid 2. So basically it goes this way all the way to 13. And you have 3 kids and number of the candy is actually 0 candy one way because no one get anything. 1 candy you got 3 way because 1 candy could get to any of 3 kids. So if you go as this way, looks like this. Then here, if you have 4 kids, then it actually follows this pattern. So follow this pattern, and because this is actually n plus 2 choose 2. So basically, we just fill in the blank for the 3 kids. N choose 2 plus 2. So for example, this is so 1 n equal to 0, 0 plus 2 choose 2 equal to 1. And the 1 plus 2 choose 2 equal to 3 choose 2 equal to 3 choose 1 equal to 3. So basically, you can just fill in here. And here, basically, we already calculated 12. 12 basically is you adding this, then we can go back to 1. Try to fill this table. 1 candy, 0 candy divided among 4 kids, that's 1. And 1 candy divided among 4 kids, that's actually going to be 4. And 2 candy divided among 4 kids, basically we're going to make this table because we're going to reduce the 4 kids distribution problem into a table of 3 kids. So basically we can just expand this table. Number of the people, number of the piece given to the first kid. Right now, let's say that we are doing the 2 candy problem. So number of the candy to give the first person, number of the remaining candy give to the 3 kids, basically going to be 2 because I'm doing 2 candy problem. And then how many ways we already solve this? So n plus 2 choose 2. So basically is 2 plus 2 choose 2, which is 4 choose 2, which is equal to 6. So basically, for this 10, basically we have one case, 6 here. Then we can also 1 candy gave to the first kids and 1 candy left to distribute among 4 kids. That's actually became 1 plus 2 choose 2, which is equal to 3 choose 2, which is equal to 3 choose 1, which is equal to 3. Then we can also give, 2 kids 2 candy to the first kid, then give 0 candy to the last 2 kids. There's actually 0 plus 2 choose 2, which is equal to 2 choose 2, which is equal to 1. So 6 plus 3 plus 1 equals to 10. So basically, this table is actually buildable. So you just, because for we already calculate out 12. 12 is our target. It's just solving the single problem, but we're trying to be general. So basically we can step it down to like 1 candy, 2 candy, 3 candy. We can figure it out. Assume you fill it out, because I don't have time to fill out all those. Assume if it's filled out, it's going to look like this. So if it looks like this, what's the property of it? So what's the property of it? You actually looks like, if you do it this way, this is level 1, level 2, this is a level 3, or level 0, level 1, level 2, level 3. This is actually exactly, the whole thing is a Pascal triangle. So if we fill this out, if we take a observation, looks like, the way to distribute to 4 kids actually is part of the Pascal triangle number. So this basically prompts us that this whole thing is actually add up to a Pascal number. So a group of Pascal triangle element will add up to another number. So this going to be the hockey stick formula we're trying to present. So how does that works into the Pascal triangle? So basically, if we write this out, if we replace this table with Pascal value, so here basically is the first element is 0 through 0, and the second number is 1 choose 1, and then this is 2 choose 2, and this side is 1 choose 0, 2 choose 0. So basically you can actually lay it out this way. So the element we are hitting is actually 15 choose 3. And so basically, if you use the smart way, basically 15 choose 3 actually will stand out right away. But assume you are not really using the smart way. But basically, if you build upon the value from this large number, from the solved problem of like 3-kid problem. So if you build up from the 3-kid problem, basically, these are the numbers add up to the 15 choose 3. And how does it look in the Pascal triangle? So basically, this is the clever way. We already teach that before. This is just stick and rock. So I'm not going to go through this one. So I'm going to just present the last beautiful piece is the identity. So this identity is actually called a hockey stick identity. So the hockey stick identity. So why it is called hockey stick identity? So let me just show so this one basically is actually 2 choose 2, add all the way up to 14 choose 2, going to be equal to 15 choose 3. So I'm going to prove it just by Pascal triangle way. So let me just copy this page and make a new page. So this is actually a very exciting result. So this is the identity. Let me just append to here. So basically what we are trying to prove is that, you know, 2 truths 2 plus 3 truths 2 plus 4 truths 2 plus all the way to 14 truths 2 is actually equal to 15 truths 3. And let's try to build out this Pascal triangle. So basically this 0 truth 0, or basically, you know, then it's actually 1 truth 0 and 1 truth 1, and 2 truths 1 and 2 truth, or 2 truths 0, 2 truths 1, and 2 truths 2. Then 3 truths 0, 3 truths 1, 3 truths 2, and 3 truths 3. And so this is 4 truths 0, 4 truths 1, 4 truths 2, 4 truths 3, 4 truths 4, and 5 truths 0, 5 truths 1, 5 truths 2, 5 truths 3, 5 truths 4, 5 truths 5. So basically, you know, and so on and so on. I'm not going to draw the whole picture, but just trying to let you understand why this is true and how it looked like. And there's a chain reaction that happen which causes this. So basically, we're going to add up this way. We are not, because this is a big number. We had to add from the top. So basically, it's 2 truths 2 plus 3 truths 2 plus 5 truths 2. So basically, it's all the way to, on the last side, basically is last layer basically is actually, you know, 14 truths, 14 truths 0, 14 truths 1, and 14 truths 2. Then this is 15 truths 0, 15 truths 1, 15 truths 2, and 15 truths 3. And here basically there's a 14 truths 3. So I'm going to just show how it works. So basically, it actually works this way. So 2 truths 2 plus 3 truths 2. Actually, there's no formula, but it happened to be 2 truths 2 is actually equal to 3 truths 3. So basically, I can replace this number by this number. So if I replace this number by this number, basically, you know, actually the first two number is addable because those are adjacent number by Pascal's identity. Those two numbers actually add up to this number. So basically, this number addition is unaddable until you find that 2 truths 2 is equal to 3 truths 3, which is both equal to 1. And so when that happens, this is the two number of the reverse triangle on the top layer will add up to the converging number of the bottom, which will, so 2 truths 2 plus 3 truths 2 actually will be equal to 4 truths 3. We can actually double check it. 2 truths 2 is actually 1. 3 truths 2 is actually equal to 3 truths 1 equal to 3. So 1 plus 3 equal to 4. So 4 truths 3 equal to 4. So basically, this actually is verifiable. So basically, then those two numbers add up to became this number, and this became 4 truths 2 plus 4 truths 3. So 4 truths 2 plus 4 truths 3 actually will converge into 5 truths 3. So basically, you know, let me just do a chain reaction illustration. So 2 choose 2. I swap this number out, became 3 choose 3. So when you add it, so once you begin to add this way, this actually became 2. So these two numbers add up 4 choose 3. 4 choose 3. Then 4 choose 3 add 4 choose 2 is actually became 5 choose 3. Then 5 choose 3 plus 5 choose 2 actually going to be 6 choose 3. So this way, basically, this for this added column, it started from 3 choose 3 all the way to 15 choose 3. So the last number is 15 choose 3, which is sum of the whole thing. So basically, this is just a chain reaction that happens this way. So the book actually has a lot of things. So basically, it's actually making a very small example. So 5 choose 2, it's actually 5 choose 2 equal to, so it's, I think it's, let me make a new page because otherwise it's going to be invisible. Let me copy this picture out and make a independent page so I can magnify it. So basically, so 5 choose 2 is actually equal to 1 choose 1 plus 2 choose 1 plus 3 choose 1 plus 4 choose 1, because 1 plus 1 choose 1 is actually will be replaced by this. So basically it looks like a hockey stick this way, but if you turn the hockey stick's head, because if you flip this number to be here, then those two numbers will add up to this number. So the addition, the sum of the previous actually follows this path, shadowing it. So shadowing it from here, then basically this will add up to here. So sum up to here will shadow to here. Then those two add up will be the final number. So basically sum of the number actually will shadow this hockey stick. So basically, so this is the first number. The first number you can, the sum of it is just itself. So you can say the first number on the hockey stick head actually the first number on the hockey stick handle actually you can, it's replaceable by the next layer. You can think as the sum of itself. So sum of the hockey stick of the previous sum is actually shadows the whole thing on the left fork. So it shadows the whole thing on the left fork from the first sum until the last sum. So basically, so that's why, that's why actually the hockey stick works this way. So sum of this row is equal to this. This hockey stick is like a long stick. So you actually can draw anything. For example, I can draw this. So 3 choose 3 plus 4 choose 3 plus 5 choose 3 equal to 6 choose 4. You can verify it. So this is actually equal to 1. This is actually equal to 4. So 5 choose 3 equal to 4. 5 choose 2, which is equal to 10. So basically, this is actually equal to 15. So 6 choose 4 equal to 6 choose 2, which is equal to 15. So basically, you can draw any hockey stick. The reason basically, see a partial sum shadows the hockey stick on the left fork. And so this is the partial sum shadows it for the first sun. For the second sun, shadows this. Third sun shadows this. Then the last sun shadows this. So basically, because of the shadow relationship, so there's a hockey stick like hitting part. This is the last turn. So how does that work? I think, you know, if you really read the formula, it's going to be very boring and very mystic and very hard to understand. But if you really just using the Pascal triangle itself and using the partial sun shadows, the each element until the last one, use this concept, it's going to be extremely easy to understand. And the way you discover this basically is listing a table and you know, map the element to be like mapping each other with the true definition of the Pascal triangle. So basically, given the observation, it actually shadows this way, and it's actually go above this. It's go way above this. So this is actually 4, you know, then for number of the 4 kids and higher number is actually the same. So basically, so this method is buildable. You actually, you know, for 3 kid, you actually can, for example, 12 kid or 3 kid actually solve to be n plus 3 through 3 because there's 12 plus 3 equal to 14 or 15. So basically then the 5 kid, you can just break down the problem into give the first kid how many, then, you know, vary that number, then you can build a similar table. Then that similar table will follow the same hockey stick. So basically, you know, like this layer, for example, this layer, 10 kid will be 11. I think this is not big enough. Let me just use a smaller one. So let's say that 5 kid is actually 6, 1. So 6, 1 is actually here. So 5 kid is actually is the hockey stick this way. And then, for example, this one is a 3 kid case. 3 kid is actually, you know, if you break down the problem into a 2 kid case, gave the first kid 0, that's 4. Gave the first kid 1 candy, that's 3 K. So basically, actually follow this stick. Then, you know, you can build this up. Then, for example, if you build up to like 5 kid, it just follow. So this is the first kid line starting from here, and then, you know, this is the two kids. So some will, so this is 2 kid. Some will actually follow this. This is 3 kid. Then 4 kid will follow this line. So it's just addition of all the previous case. Then 5 kid will follow this line. So basically, you know, it's actually hockey stick. You can build up everything this way. Then if you are able to build up things this way, it actually eventually you actually prove that using this method, you can prove that, you know, it's for for M kid and the M candy, it's just follow the clever method of stick on rock. So basically, eventually, even you use a different method, I use a dumb method, but the dumb method basically, given the hockey stick and given the way it add, eventually it just proves that, that's m plus m minus 1 choose m is the way that of the solution to any number of the kids, any number of the candy. So that's the way that, the whole thing. So I think it's quite exciting, but anyways, this is a really long lesson because I have to explain really clearly. Hopefully you understand what I explained. And if you don't understand, hopefully you can just review the video. And so it's so the quintessential meaning is just, for the Pascal triangle. Let's do a summary. So what's the Pascal triangle? Fun thing is that it's just the reverse triangle. This is the Pascal's identity. Then hockey stick is just a chain reaction of the whole thing. Because if you just put the number one thing lower as the partial sum, you begin to experience this chain reaction, which make the hockey stick works. And the also that's the knowledge for the Pascal triangle itself. And then also we're talking about the method to break down a harder problem. For example, distributes that many candy actually has two variable, number of the candy, number of the kids. By vary number of the candy, the problem goes nowhere because the pattern changes dramatically through number of the candy. But if we use the number of the kids, looks like it's a buildable problem because every one more kid you add, you actually can break down the problem into, give certain number of the candy to one less kid, then the total count is just addition of all the cases. Then basically, this became a buildable problem which actually add up to nicely fitting into the table of the Pascal triangle. So it's actually fitting into the Pascal triangle. That's the first hint that there might be something bigger underlying. So given this pattern, so then we're trying to identify the number on the Pascal triangle itself. Then we discover the chain reaction. After we finding the chain reaction, then we actually find the identity, which is I'm not really recommending you to remember this identity. Hockey stick, how do you remember it? You just draw it on the Pascal triangle itself. The hockey stick basically actually draw from the hockey stick, basically the hockey stick actually draw from top right extreme. It's hitting at the edge, need to hitting the edge, then follow the line, then it's going to just shadow it to the hockey stick head turn. So this is the head turn. Head turn, the reason is that partial sum shadows the whole thing one line below on the right fork. So basically, because this hockey stick theorem actually follows the left fork line. So this is the left fork. The left fork line actually will keep the lower number. Left fork will keep the lower number. So the lower number. So how do you identify a hockey stick situation? If the combination number truth value is the same, that's a hockey stick. especially start from the head, which, top hand, then it's going to make a turn. And the formula itself is quite big. I never tried, because if you're trying to remember the formula and not understanding it, you will never really get it, because it's too complicated. Because Pascal Pascal identity also is something that, so basically, how do you identify the hockey stick theorem identity? Because it's left forking, the lower value is always the same. Then the top is just, it need to start from the same value, because it hit the extreme. It just keep adding the layer until then basically it's making, so this is the last element. So the sum is going to be the right fork. So sum is the right fork of last value. So the last value, so right fork going to add a layer. So the layer add 1, and right fork going to add a truth number by 1. So basically both add 1. So how do you identify a hockey stick? On the addends, because it's left forking, so the truth value going to stay the constant. Then the layer start from the truth value on the top, then go all the way down. The sum, where's the sum? The sum going to be a right fork of the last number. Right fork of the last number, just layer add 1 and the truth number add 1. So it's very, very simple. If you understand the mechanism of the whole thing, it's very easy to, remember. I don't remember it. I sincerely, I just, draw it. I draw it, I understand it's, the sum is the right fork of the last value, so I can actually identify those problems very easily. Okay, I think that's all for today, and I think you're going to do all the homework. Okay, have a nice one. Bye bye.
Bye. Thanks.
Thank you.